top drawer of that container, there's a bunch of pens and pencils.
You don't expect me to stare straight the whole time. Yeah. Pay attention.
Can we put laptops away, please? I see there were multiple of them out. Yes. Chapter 2 is the beginning of our quadratics sections. We do quadratics actually in a couple of chapters. There's chapter 2 and chapter 3. They both kind of focus on different things with quadratics. What makes an equation quadratic? The squared. It's got x squared in it, and more specifically that is its highest exponent. Now, yesterday we explored things that were quadratic, specifically that were in what's known as vertex form for quadratic equations. F of x is equal to a times x minus h in parentheses squared plus k. Now here's the thing, we've done transformations in this class already, but I am also well aware that transformations was the most common area in which we struggled in chapter 1. But so much of that struggle with transformations early in chapter 1 tends to have a relation to the fact that because we're dealing with any type of function, I have to explain things using function notation and how that deals with the various things. And function notation, while a fantastic tool, and while it is something that we should be solid on, I'll be honest, we don't quite have as much solid of a foundation on it, and it leads to the abstraction of chapter 1 being harder than when we get into the more specifics. Okay, those of you who kind of are like, you just spoke a bunch of words, but I don't know what you're saying, the short end of it is transformations in this chapter tends to feel easier. So, vertex form. A, H, and K are coming back because we are graphing our quadratic equations, making our quadratic graphs. Do you guys remember what a quadratic graph, that U-shaped graph, is called?
Nope.
Starts with a P. Parabola. So, vertex form, graphing, we've got our parabolas that we're looking at. Now, I am going to write here with a little bit of space above and below because I'm going to write above and below it. I'm going to write out my vertex form again, nice and big so I can label things on it. The things that this form does as compared to what we talked about in chapter 1 is all the same things. We added and subtracted things. Sometimes inside of the operation, inside the parentheses, sometimes outside of the parentheses. Do we remember what adding or subtracting inside does to the graphs? Moves it either left or right. Now remember, inside the parentheses is always a little bit backwards. Left is by adding. Right is by subtracting. What about if it was outside the parentheses? Up and down. This does exactly what you would expect. Up if added, down if subtracted. Now we could also put things in front of our functions. We could put two different types of things in front of our functions. if we put it very much in the front, and if it's negative that we put in front, what does it do? Flips it across which axis if it's all the way in the very front?
X.
Yes. Ignoring the negative, if we put a number in front of the entire function, what is the other thing it can do? Stretch or? What type of stretch or shrink, though? Vertical stretches and shrinks. Now, when you're dealing with vertical stretch or shrink, you are ignoring the negative. The negative is that flip. If it's a negative number in front, you just look at the digit. And so, essentially, it's as if the things are an absolute value. If the number is bigger than 1, is that a vertical stretch or vertical shrink? Say it with some confidence. Stretch. And then you tended to see me on answer keys put F. It means factor of that absolute value of A, of whatever number you're multiplying by. That being said, if the number is smaller than 1, it is a vertical shrink. The factor still being that absolute value of A. Now, we talked about all of these things back in chapter 1. There's one more thing that we talked about in chapter 1 that I haven't talked about here. Okay, kind of two, actually. Horizontal stretches and shrinks, horizontal reflections. Those typically happened in front of the X inside the parentheses. Those would have happened right here. Now, you'll notice I changed colors because there's not technically anything in front of that X right now. In vertex form, that shouldn't have anything in front of it. If it does, it can cause issues. If there is a number there, it can mess with the vertex. It messes with the vertex because of the fact that it all of a sudden is either reflecting across the y-axis or it has a horizontal stretch or shrink. Now, let's say the number there, if there is one, is equal to b. Let's just use b as a reference because I don't want to use A again, even though it technically was A when we talked about it in chapter 1, because A just represents stretches and shrinks in general. But for the sake of talking a little bit separately about it, I want to call it B. If B is negative, technically that is a reflection across the y-axis. Now, here's where this one always became a little weird. Anything in the parentheses did some things a little bit backwards. Left seems like it should be right, right seems like it should be left. We also have the issue with that horizontal stretch and shrink. Specifically, its factor is B's reciprocal.
AKA it's 1 over b. That's what b's reciprocal would be. And to figure out horizontal stretch or shrink, you have to look at the factor. The stretch happens when that reciprocal is greater than 1. The shrink happens when that reciprocal is smaller than 1. Now, since it's a reciprocal, the reciprocal of a number bigger than 1 is smaller than 1, and the reciprocal of a number that's smaller than 1 becomes bigger than 1. So it always seems opposite. If there was a 2 in front of the x, that would be a shrink. If there was a 1/2 in front of the x right here, that would be a stretch. Now that being said, we're not going to deal a whole lot with the horizontal stretches and shrinks. We are going to take care of those in a slightly different way today because we're going to modify into vertex form. That is to say that's when we get there. When those pop up. So today instructions are going to look like this. Describe the transformations in order to sketch the graph. ID the vertex, domain, and range. Sorry, I didn't realize my volume was off. Okay, now when it says describe the transformations, if it doesn't tell you from what, it's assuming to the parent function, to the most basic of the functions. The most basic function in any family, save for the constants, that's its own deal, really just is a function that only has the thing that makes it that function with no numbers. In this case, x squared, just plain x squared. Okay. If we want to identify the transformations, we're going to look for basic things like, you're going to essentially go through 4 questions. Okay, 5. First off, is it in vertex form? 99% of the time it will be. The only time it won't be, I will address that towards the end. If it's in vertex form, then you look for the movements. Did it move up or down? Up, how much? Up 3. Did it move left or right is the third question. No. Now you don't have to write no left and right when it doesn't actually do the item. I do it for the sake of our notes. If you do it every time, go for it. So, but there was no left or right movement. Does it flip over? No flip, no reflection. Does it stretch or shrink? Stretch or shrink, we're looking for the number in front of x squared. There isn't one, which means there's no stretch or shrink. The only thing this one did was moved up 3. Make sure on your graphs you are putting tick marks. on the axes, I will assume that if you are counting by one, or sorry, let me rephrase that. I will assume you are counting by one unless you put numbers on them. Yesterday, the first thing that I had you do is I had you focus on f of x is equal to x squared. And I said, find some key points that that graph hits. Where did f of x equals x squared hit? What were some key points it hit? Coordinate points have two numbers. Huh? 0, 0. Were there any others? Yes, there's an infinite number. 1, 1. There's one other that I wanted you to focus on. Negative 1, 1. Essentially, the parent function, which you don't have to graph here, but I'm going to graph it in pencil just for reference. Hit 0, 0, one diagonal in each direction, and then it made a U shape, connecting that. That's the graph you're moving. In this case, moving up 3. Take this point, move it up 3. 1, 2, 3. Since nothing else happened, then technically it should have a point kind of here, kind of here. Now, I'm not looking for your graphs to be perfect. But by putting those points on there, it can kind of help you get the shape of the graph without going too wide or too narrow. That's why I do it. There's my graph. Have we finished the problem? No. It wants to know where the vertex is, the domain and range. What the heck is a vertex?
It's the bottom that changes the U.
In this case, it's the bottom part of the U. It's the part where it changes directions. Vertex, by definition, is the highest or lowest point. What is the coordinates of that point? 0, 3. Ta-da, you've identified the vertex. Domain for quadratics. Really easy. Goes all the way to the left. It goes all the way to the right. It hits everything in between. Domain for quadratics is always all real numbers. Range. Not quite as easy. But it shouldn't be particularly hard. You just have to look. Is my graph opening upwards or opening downwards? Opening upwards. The graph is going up. As you go up, do numbers get bigger or smaller? Bigger. Which means y's are getting greater than or equal to, and I was told 3. Where'd the 3 come from? Y value of the vertex. G of x is equal to negative, parentheses, x minus 4, close that square, plus 1. Technically, we need to make sure it's in vertex form. When you're making sure it's in vertex form, both this one and the last one are in vertex form. I've got things being squared, could be parentheses, there might just not be parentheses. There's things being added and subtracted. The only thing that would really make it not vertex form is what I mentioned earlier that will mess with things. If there's a number directly in front of x. Is there a number directly in front of x? No. Vertex form. I'm not trying to trick you guys with this. Look for if there's a number in front of x. If there's a number in front of x, it's not vertex form. Okay, once you've noticed that it's vertex form, ask yourself about the movements. Did it move up or down? Yes, which one? How much?
1.
Did it move left or right?
Yeah.
Yes, how much? 4. Did it flip over? There's a negative in front. That's a reflect across the x-axis. Did it stretch or shrink? No. There's no number other than 1 hiding in front of the parentheses. Now, technically it's a negative, but for stretch or shrink, you ignore the negative and just look at the digit. The number that hides after a negative symbol, but in between things, is a 1. So, no stretch or shrink. So I go to my axis, giving myself a little bit more room to the right, maybe a little bit more room above, because that's how it moves. This time around, I'm not going to draw the parent. I'm going to go directly to our graph. I do have to reference the parent. The parent hits what is the most important point? 0, 0. That's the parent's vertex. From 0, 0, I need to move up 1, right 4. That's my new vertex. Up 1, right 4. Vertex. Now I need to make my U. There's no stretch or shrink, so I don't have to worry about skinny or wide. But it does flip over, which means instead of opening up like an upwards U, it's upside down. Now, if you're wanting to make sure you don't get it too wide or too narrow, something that has no stretch or shrink just goes 1 diagonal. I'm not looking for perfect. So if it's not perfectly 1 diagonal, it's not the end of the world. Where's my vertex? Four, 1. Domain for quadratics is always the same thing. It's always what? All real numbers. Range. Range has to deal with y. It's going down, so it's less than or equal to. The number that it's smaller than is going to be 1. Because it's the y value of the vertex every time. Okay. Is this one in vertex form? Is there a number in front of x? A number in front of x means not vertex form. Now, just want to backtrack a little. I'm going to focus on this problem first to just kind of point something out to you. Why do you think vertex form is called vertex form? Go for it. It starts at the vertex. It actually tells you where the vertex is located. Look at my vertex here. It's 4, 1. Do you see 4, 1 in your equation? Now that's -4, so it's opposite. But here's where that came from. The 1 came from. So 4, 1 I could have come up with from the equation. Could we have done the same thing here? Inside parentheses that don't exist, what would have been added or subtracted if nothing is there? 0. What's the opposite of 0? 0. Outside is the 3. Hence the vertex at 0, 3. In fact, when you go work with vertex form, the vertex, that highest or lowest point, is at HK. Now, notice that in the formula, it has a minus for H. That's what tells us that we actually look at the opposite of the number. Now I bring this up because that is actually going to be the thing that helps us graph this one. Because when it comes to graphing these, and we focus in on these key things, you'll notice that up, down, left, and right, those go back to what the vertex did. So if you can identify the vertex without having to think up, down, left, and right, it tells you the up, down, left, and right by just telling you where that point is. Flipping over is an easy thing to look for. Stretches or shrinks, I'm not looking for anything fantastic. So, when you have the situation where you have something that's not in vertex form, you're actually better off finding the vertex first by modifying it to vertex form. What modifies it to vertex form is you take what's in the parentheses and divide out the b value. Now keep in mind, this is not to change the equation. The equation still is as the equation is. It is still 3 parentheses negative x plus 1, close that parentheses square. Dividing that, in this case, negative 1/2 out is not going to change that. I just do that to manipulate my problem to get what I want. So I take this negative 1/2 x plus 1. This right here is what I'm referring to as b, and I divide it out. Divide by negative 1/2. If you divide one thing, you divide everything. I get positive x. Positive divided by a negative is negative. What is 1 divided by 1/2? Try again. 2. Divided by a fraction, keep, change, flip. That look familiar? To divide by fractions, you multiply by the reciprocal. Worst case scenario, can you divide in your calculator? Yes, just make sure the negative 1/2 is in parentheses. But if I was to type that into my calculator, any old calculator, 1 divided by negative 1/2 is negative 2. This now becomes the h that we're subtracting, which means our vertex of this graph will pull its x value from this. Now, just like we did on the previous ones, When you're looking at that, you don't look at that number directly, you look at its opposite. Not reciprocal, opposite. What's the opposite of negative 2? 2. Once you have the vertex, you can graph from there. Now I still am missing a part of my vertex. The second part of my vertex came from the plus k. Did I add anything to this one? No. What number gets added if you add nothing? 0. My vertex is at 2, 0. I can plot that point on a graph. Will this graph open upwards or downwards? In other words, did it flip over? If it did not flip over, does it open up or down? Opens up. What's that 3 do? Vertical stretch. When you stretch something vertically, does it get skinnier or wider? Skinnier. I got a skinny graph that goes upwards, where that is 2, 0. I'm not looking for these graphs to be perfect. And you can essentially always look for the vertex first. I wanted you to reference the transformations on the first couple problems because I didn't just want you to type it into a calculator. Do you notice I didn't write down what a single transformation was? Because I'm not actually all that worried about you telling me the transformations this chapter. I'm getting the vertex needs to be in the right place, it needs to open the right direction, and try to make it narrow or skinny appropriately. We're going to do just one final example. This last example, I'm going to do the way that we just did. Because in the end, that will be the easier way to do it, if you can master it. G of x is equal to 2/3 parentheses x minus 4 quantity squared minus 2. Is this in vertex form? Yes, there's not a number here. If it's in vertex form, you should be able to tell me where the vertex is without having to do any graphing. What's the x value of the vertex? Positive 4 or negative 4? Positive. Remember to do opposite. So positive 4. What's the y value of the vertex? Negative 2. Plot the coordinate point 4, negative 2. So 4 to the right, down 2. It's right there. Is my graph going to open upwards or downwards? Why up? It didn't get flipped over. Technically, it's got a 2/3 there. Is that a shrink or a stretch? Shrink. When you shrink vertically, it makes it wider. So I make a wide graph that goes upwards. That's all I'm looking for. I'm not looking for any of the specifics. I'm not actually looking for you to tell me up, down, left, right. We did the up, down, left, right just to kind of get to the idea of this is how you find the vertex. Domain would be all real numbers. Range would be y is greater than or equal to negative 2. Opens up, greater than or equal to. Opens down, less than or equal to. Okay, I spoke far long enough. Las stickies. Page 50. Numbers 1 through 9, the odds, and then 11 through 22.